If we have a battery, light and switch placed on the Earth and cables connecting them together go to the moon and back, how long does it take the light to go on when you turn on the switch? That is basically the question what Veritasium asked in his The Big Misconception About Electricity video. After watching that video, I had to keep thinking about it. So I had a call with Eric Bogatin, which I recorded, and where Eric explained what is going to happen when you turn on the switch. Before we start, these are the circuits what we are going to talk about. They are very similar to the original circuit used in the Veritasium's video, and these two circuits are basically the same, just the components are placed differently. And that's everything what you need to know, so here is my call with Eric. So it's basically exactly same circuit, but the bottom one is the one what he used in the video. And he said the ends of these tracks or wires, they will be like very, very far away. And he said like when you press the switch, the light will go immediately on. But on the top picture, I created exactly same circuit, just move it a little bit. And in my mind, this looks like our standard PCB, what we normally do. And you know, when you press the switch, in my mind, it should be what
I mean, it's the same circuit topology. It's just moved in a slightly different orientation. I like the one on the top because I think that describes the behaviors much better, and it's easier to think about. So if we understand the top one, the bottom one will apply directly.
Oh, we can start with this. So you understand the pictures, yeah? Basically, the green area, you can imagine this as a PCB, okay? The yellow could be like tracks on this PCB.
Yep.
And the symbols are the components on the PCB.
Yeah, so here's the driver, and here's the output pin of the driver that we're going to turn on.
Exactly.
And then here's an LED that's at the end of the transmission line.
Yes, exactly.
Yeah. Okay. Now, can I offer a slightly modified version of this to talk about, because it relates directly to how to think about signals on a transmission line. Okay. Well, let's see if this is going to work. So you can see my whiteboard here?
Yes, I can.
Okay. So here's the problem I'm gonna create. So here is a simple transmission line on a circuit board, and I'm going to put the plane down below underneath it. And we're going to come over here at the beginning of the line, and here's the return plane next to it. And let's make this transmission line, let's make it, let's say 6 inches. And you remember what the time delay for a 6-inch long transmission line is, going down from one end to the other? If I launch a signal in the front end, how long does it take to go down and reach the end of the line?
I don't remember that number.
Okay, really easy to remember. That's why I was like 6 inches. In air, it's 1 foot per nanosecond is the speed, 1 foot per nanosecond in air.
That really doesn't help for people who
30
are
centimeters. 30 centimeters per nanosecond in air. And then you throw in the dielectric constant, it cuts it in half. It's about 15 centimeters per nanosecond, which is 6 inches per nanosecond. So if it's 15 centimeters long, then it takes about 1 nanosecond to go down and back. Okay, and now we ask the question, okay, I come into the beginning here and I launch we're gonna make this a 50 ohm transmission line. Now I ask the question, when I come in the beginning and I launch a 1 volt signal, peak to peak, 0 to 1 volt signal into this transmission line, here's this edge that's going to move down the transmission line. When I launch that 1 volt signal into the transmission line, it's a 50 ohm impedance. That means that there's a current draw of, let's see, the current is going to be the voltage over the resistance. It's 1 volt divided by 50 ohms. So that's 20 milliamps. So I'm going to send 20 milliamps into this transmission line. Now the question is, and it takes a nanosecond for the signal to go down, nanosecond for the signal to come back. The question is, I launch 20 milliamps in the beginning of the transmission line. When do I see 20 milliamps come out? Okay, very similar kind of question to what's posed in the other video. So when does the 20 milliamps come out of the return path?
Oh, it will be there all the time when it's traveling, no?
Really?
No, I don't know. I'm wrong.
But how does the current go all the way down and then it has to come all the way back again? I'm putting 20 milliamps into the transmission line at the launch. How does it come back out
Because
so
of
quickly?
the displacement current, no?
Oh, you see, I can't put anything past you anymore. You have learned all of the secrets to interconnects. You are exactly right that I put 20 milliamps in, I'm going to get 20 milliamps out instantaneously. The same instant I put the 20, I get it coming out. And the question is, how is that possible? Because current continuity of current has to travel in a loop. And between the signal over here and the return underneath here, I have this insulating dielectric. How do you get 20 milliamps going through the transmission line back through this insulating dielectric? I mean, you get 20 milliamps flowing as a loop, but how does it come back? And that is a real stumbling block unless you understand a key element in electromagnetics related to displacement current. And I think the fellow in the video kind of alluded to that. And it is one of the key advances that James Clerk Maxwell made in unifying all these separate different concepts about electric and magnetic fields. And that was really one of the two innovations that he implemented to unify the equations, get a simplified version, and relate about how signals propagate in free space and on interconnects as well. And so how do you get current flowing through an insulating dielectric? And the answer is displacement current. And so when I launch my voltage in the transmission line, I've got a voltage change between the signal and the return. That voltage is going from 0 to 1 volt in some rise time, some short period of time. And that means I have a changing voltage in that location where that leading edge is located. And by changing that voltage, I mean, you can think of it in terms of capacitor. I've got a little bit of capacitance in that footstep right here where that signal's launched. I have a little bit of capacitance. And if I have a capacitor, we think about a capacitor as two conductors, insulating dielectric between them. There's no connection between the two plates of the capacitor. How do you get current through a capacitor? And the answer, DC, you don't. But if I change the voltage across the capacitor, I do get current. And the charge across the plates of a capacitor is C. The charge, excess charge on the plates is C times the voltage. And so how do you get current through there? Well, if the voltage changes, the charge changes. And so the only way we get current through the capacitor is if you have a changing voltage. And how does it do that? I mean, there's an insulating dielectric between here. How do you get current through the capacitor? And this is Maxwell's innovation contribution that he said, inside, if I have vacuum in there, no material at all, inside there, if I have a changing voltage, I have an electric field between the two conductors. And if the voltage changes, the electric field inside the conductor changes. And he said, just as real a kind of current as conduction current is a new kind of current, which he called displacement current. And that is related to how fast the electric field changes. And so whenever you have electric field changing, even if you have no conduction charge, so we separate out current from of free charges flowing, that's one type of current, conduction current. And here's this brand new type of current that has nothing to do with charges moving, but it is changing electric field we call displacement current. And so how do you get current from the going through a capacitor is by changing the voltage across the plates, increasing and decreasing the voltage. If you increase the voltage, you add some more plus charges to the top. You're throwing away, you're pushing out plus charges from the bottom. So you have current flowing in, current flowing out. And in between, in this region where we have the no material at all, we have changing electric field. And that's how we get continuity of current through the changing electric field, Maxwell called displacement current. And that's exactly what happens between the signal and the return as that edge moves down the transmission line. Wherever we have the changing voltage, that's where we have the changing electric field, and that's where we have displacement current. So we have conduction current flowing down the transmission line, displacement current flowing through, and conduction flowing. And so that signal propagating down the transmission line is this wavefront of displacement current propagating down the transmission line. So this is exactly like the case that I just showed. At t equals 0, the switch is open. So here's the plus over here. This is where the driver is. And then here is the other side of the line, ground, 0. And then here's way over here is the LED over here. And so right now, this instant between the signal and the return, we'll call the bottom guy the return, the top guy the signal. Right over here between the signal and the return, what's the voltage between the signal and the return conductor? What's that voltage difference?
When it is open?
Yep, right now initially t equals 0.
There is no voltage difference, it's 0.
Right, 0 voltage.
Yeah.
Right now, between over here on the other side of the switch, between the signal and the return, right here, what's the voltage?
Yeah, there is the battery voltage.
1 volt, let's call it. Yeah, right. And so now we throw the switch. And so what we're going to do is we're going to suddenly change the voltage between the signal and the return here. We're going to increase that voltage. And so and to put in some numbers just so we can think about what's going on, let's assume that these are 2 conductors, signal and return, and any 2 conductors, especially when they're nice and uniform, but any 2 conductors spatially separated create a transmission line. And if they're uniform, cross-section stays the same, there is a constant instantaneous impedance each step along the way as I walk down this line. And let's, just so we have numbers, let's call this, suppose this is a 50 ohm transmission line. So the instantaneous impedance each step along the way, 50 ohms. And let's suppose that, again, just to put in some numbers, here our source impedance, the source resistance, make that 50 ohms as well. So and this is a 1 volt line. No, I'm sorry, let's make it a 2 volt and make the numbers easy. This is a 2 volt battery. So here's 2 volts between the signal and return right here, and here is the 0 volts. Now I throw the switch. When I look into this so it's the same exact problem we just looked at. I initially turn this voltage on. Let's see. There's a voltage divider between the 50 ohm and the 50 ohms here. I get 2 volts, so there's going to be 1 volt launched into this transmission line. And 1 volt and 50 ohms, that's 20 milliamps. So I get 20 milliamps of current going into this transmission line. And what do I have in the other end of the line that's moving this way? I have 20 milliamps of current. And so I have a signal return, signal return. I have 20 milliamps of current flowing through the displacement, the changing electric field between the signal and the return right here. So it's signal return, signal return, signal return. So 20 milliamps goes in, 20 milliamps comes out, and it gets back here. This is really short electrically. It gets back here really quick. So, but that wavefront of displacement has to travel all the way down here. And while it's traveling there, this poor LED has absolutely no knowledge that anything happened over here. And let's make this 300,000 kilometers, and we'll make it in vacuum in space. So this is a cable that goes between the Earth and the Moon. And it takes about a second. Actually, the Moon is, I think, about 450,000 kilometers. So it's about 1.5 seconds to go down and back, 3-second round trip time. So it's going to take 1.5 seconds for that signal to go all the way down. It's traveling, it's signal return, 20 milliamps, 20 milliamps, 20 milliamps, 20 milliamps, turns on. And so 1.5 seconds after I throw the switch, the LED turns on. But when did I get my 20 milliamps of current coming out here? As soon as I threw the switch right here. Okay, so this part Pretty clear, right?
Yeah.
Now, while we're here, let me ask the question. I said, hey, here's a transmission. It's a coax cable, a giant, really, really long coax cable, spans from the Earth to the Moon. And I said its characteristic impedance was 50 ohms. That means that when I launch a signal, that instantaneous, it's uniform. Everywhere down the line, I see the same instantaneous impedance, and that one value of instantaneous impedance characterizes the transmission. That's why we call it the characteristic impedance. So that is the instantaneous impedance. So now suppose that instead of putting the LED over here, suppose I just left this connection open. So there's no path for the current to flow between the signal and return over here. It's an open. I pulled the LED out of its socket on the moon. Now I come over here. I'm here on the Earth. I'm looking in the beginning. It's a 50 ohm impedance line. Instantaneous means 50 ohms. I look at the beginning of this line, and I look at that, and I grab my ohm meter from the shelf. And my ohm meter basically does this. It launches a current into the device under test and measures, applies a voltage across it, measures the current through the device. So it's going to launch a voltage, measure that voltage at the beginning, and it's going to measure how much current's going into that circuit. That's how the ohm meter works, right? So I connect a 1 volt source to the transmission line, to the beginning signal and return, connect a 1 volt across it. I measure the current coming from that 1 volt source, and that ratio of voltage to current gives me the impedance going in. It's open at the far end here. What am I going to measure on my ohm meter? So I come over here. Here's my ohm meter. I'm going to see if I can draw this. My ohm meter is a voltmeter and an ammeter. And this is literally a little handheld digital multimeter set on ohm scale, and it applies a 1 volt signal and measures the current coming out. Okay, and the resistance that I read on the scale is the 1 volt divided by the current that's coming out of the ohm meter into my device under test. Now, if I came to my lab, and so I've got this little cable here. I don't know if you can see it, short little coax cable. And if I came to my lab and I took my ohm meter and I connected between the signal and the return on my little 1 foot long cable, or my 30 centimeter cable, of course, what would the ohm meter read? And the end, of course, is open over here. What would the ohm meter read when I connect between the signal and the return my 30 centimeter long cable?
Nothing.
It'd be, you mean 0?
Very high impedance.
Very high, right?
Resistance.
It'd be an open.
Yeah.
It'd be an open. Resistance is open, right? But now I've taken that cable and I've made it 450,000 kilometers long, stretching the Earth to the Moon. It takes 3 seconds for a signal to go down to the end and then come back, right? So now what does my ohm meter read? Because, and the ohm meter, these ohm meters are pretty fast these days. It updates every half a second. And so when I connect my ohm meter between the front of my transmission line, I can do a reading in a half a second, and every half a second thereafter. What will my ohm meter read? This is one of those really simple concepts that really challenge our fundamental understanding, intuition. So it updates every 0.5 seconds, and it takes from here to here, because this is the moon, it takes 1 nanos, no, I'm sorry. Let me see if I can do my eraser here. It takes 1 second as the one-way time delay. So what's my ohm meter going to read? So I got this really long cable. I'm looking on the front end. I stick my ohm meter between the signal and the return. What's it going to read? When it was really short, it was an open, right? When it's really long, what's it going to read? Well, when I connect the end of my ohm meter to the end of the cable, I apply a 1 volt signal. What is that 1 volt signal? Initially, what is that instantaneous impedance that I see as soon as I connect that 1 volt signal between the signal and return? Well, I see an impedance of 50 ohms. And so initially, I'm going to get, let's see, 1 volt into 50, I'm going to get 20 milliamps. And what is that 20 milliamps of current? What's that that voltage wavefront. I just increase the voltage here. What's that voltage signal going to do? That 1 volt signal is going to propagate. It's going to zip down this very long transmission line there, because that is the second innovation that Maxwell introduced, this idea that if I have a changing electric field, so I've increased the voltage, I've increased the electric field in that region between the signal and the return, that changing electric field generates a changing magnetic field, the changing magnetic field generates a changing electric field, and it self-propagates.
So it's
and
going to read like 50 ohms?
It is. I'm going to get that signal propagating down the transmission line at the speed of light in the vacuum of the coax cable. It's going to propagate it at 30 centimeters per nanosecond. It's going to zip down that line, and in its wake, it's going to leave. It's going to be a signal going in, a return, signal, return, signal, return. It's going to be the signal propagating down as conduction current.
Okay, now
wherever I have that changing electric field.
I know where you are going with this.
And so what do I see going in here? I launch a signal, 20 milliamps comes in, 20 milliamps comes out. My voltmeter applies a constant 1 volt. It reads 20 milliamps going this way, 20 milliamps going this way. And I say, oh, the input resistance, because that's all my ohm meter reads, the input resistance is 50 ohms. But wait a minute, it's open over here. I left it, I pulled that LED out, it's open. How is it possible for me to attach my my ohm meter and measure 50 ohms when it's open at the far end? And that's because the input impedance of this transmission line changes. If I initially connect my ohm meter, and I launch that 1 volt signal down that line, it takes 1 second to go down. What's it going to do when it hits the open? It's going to reflect, and now it's going to be a 1 volt going this way, and it's going to be a signal return, signal return, signal return. It's going to propagate in the other direction. It's going to take another second to come down, and now let's see, this current's moving this way initially. The return current is going to go the other way. These two currents are going to cancel out, and suddenly, as soon as the reflection gets here, and it's at 50 ohms over here in the source, as soon as it gets here, those two currents are going to cancel out. And if I look over time, and I look at the input impedance, input resistance versus time, I turn on, I'm going to get 50 ohms, 50 ohms, 50 ohms, and then 1 second to go down, 1 second to come back. So here's the 1 second mark, here's the 2 second mark, and then it's going to be infinite after 2 seconds. The input impedance of that cable changes based on how long it takes for that signal to go down and back. And now let's go back to, so here it is between the Earth and the Moon, 450,000 kilometers, 1 second one-way time delay, 2 second round trip time. In those 2 seconds that I'm doing the measurement, my very slow digital multimeter, my very slow ohm meter, is going to measure the input resistance 50 ohms, literally with an ohm meter, because that's how it behaves. It looks like a resistor at the front end, because I have a constant voltage applied and a constant current, and that is the very definition of a resistor. If I have an ohm meter that's really slow, that takes a half a second to work, I have to have a transmission line that's at least 1 second, at least a half a second time delay in order for me to see the resistance of the front end with my slow ohm meter. The shorter I make that cable, the shorter time I have to measure that constant input impedance or resistance. And now I go back to Earth or lab scale dimensions. If I have only 30 centimeters long, or if I have 1 meter long, 1 meter long, that's in air, 1 meter long, that's 3 nanoseconds to go down, 3 nanoseconds to come back. In order to measure that constant input resistance, I need an ohm meter that can do a measurement in a time short compared to 3 nanoseconds down, short compared to 6 nanoseconds. I need an ohm meter that can measure that resistance in 1 or 2 nanoseconds. And you can't use a handheld digital multimeter to do that. You need a really, really fast ohmmeter to do that. And that's kind of what a TDR does. It's a really, really fast ohmmeter and can measure that input impedance in a time short compared to the round trip time for the signal. But this concept of the finite speed of a signal and the idea that it propagates down a transmission line, and what propagates is not just the voltage, it's that current wavefront as well. Now, this model that I like to use, this is a transmission line model. It describes a transmission line is a circuit element, and it describes unlike a resistor or a capacitor or inductor that are lumped circuit elements, that their properties are all confined in a point. That's why they call them lumped properties. A transmission line, we describe it as a distributed circuit element, in that its properties are distributed throughout its length, and there's a time delay associated with it. It's still a circuit element, but I've been talking about words like the voltage on the transmission line and the current through it, and these are kind of approximations, because just describing the voltage and the current really doesn't describe the fundamental physics of what's going on. And that was the point that the fellow made in the video about, his terms were, we've been lied about how electricity travels on transmission lines. Now, he was referring to transmission lines as the great big power transmission lines. I use transmission lines describing our traces on a circuit board, but they're kind of the same thing. They are two or more conductors with some spatial extent and some extended length. And he's absolutely right that the real world really is described by fields and Maxwell's equations. And I want to, maybe you can reference this in your show notes. I wrote an editorial, it was in last January, for Signal Integrity. So I'm technical editor of Signal Integrity Journal, and I invite all of your viewers to visit signalintegrityjournal.com. It's a lot of words to type in there. But we focus on technical articles in this whole field of signal integrity, power integrity, and EMI. And I wrote an editorial for our print edition in last January about that the real world really is described by fields, magnetic electric fields, as described in terms of Maxwell's equations. And that if you really want to understand how signals interact with interconnects, you really have to go back to understand the basics of how fields interact with materials, and they're described mathematically, Maxwell's equations. And, I get a lot of people whenever I talk about, Maxwell's equations and the theory of electromagnetic fields, everybody always says, oh, those are just theories. And, how do we know they're true? Well, it turns out that the combination of Maxwell's equations and quantum mechanics, two Maxwell's equations revelation of the late 1800s, quantum mechanics revelation of the early 1900s, and then you throw in special relativity from the first part of the 20th century. Those three pieces of physics comprise altogether, they're lumped into this field called quantum electrodynamics. And if you want to, learn some very highfalutin sounding jargon, quantum electrodynamics is the marriage of Maxwell's equations, of special relativity, and quantum mechanics. And those three combined together represent the best model we have of how the real world behaves. And how well does that model predict the behavior in the world? So far, we have never found a single experiment that's been done whose results conflict with or are not consistent with the quantum electrodynamics. And the best measure in any experiment that's been done, the best measurement that's been done is of what's called the G factor of the electron. This has to do with the magnetic field of the electron and how it spins. We have measured the G factor of the electron to 12 decimal places. And we can calculate what should that number be based from just sitting in a windowless room and just with pencil and paper and just calculating what should that number be? We can calculate it to 12 decimal places. And you know what? Those numbers agree in the 12th decimal place to within the uncertainty in that 12th decimal place of the measurement of the G factor of the electron. Those two numbers match each other. I think that's why I became a physicist, because it is incredible that you can come up with a model of how the universe behaves and go and measure it, and darned if they don't agree. But going back to Maxwell's equations, that's why Maxwell's equations are so powerful. Here's the problem. I use that term quantum electrodynamics, a really big mouthful of technical terms. Maxwell's equations themselves are very daunting. We spend literally years in college studying Maxwell's equations. I have one of my graduate students right now. He's taking the graduate level class on electromagnetic fields and Maxwell's equations. He's sharpest graduate student I've had. He's pulling out his hair, struggling to do all the calculations with Maxwell's equations from this class. Sharpest electrical engineering graduate student I've had for a while. It's really hard to do anything other than the simplest calculation with Maxwell's equations, even though they are the accurate description of the real world. Really hard to use. And so we approximate Maxwell's equations, and we have to be a little careful in believing the approximations as what is reality rather than the behavior fields. And that is where the confusion arises. It's in using approximations, because we can do calculations with them pretty quickly and easily. We can understand that we can build an intuitive model that will help us solve problems quickly using the approximations, but they're not quite the real world. And so and I had a professor once, Victor Weisskopf, very famous Austrian physicist, one of the fathers of quantum mechanics. I had him as an undergraduate 50 years ago. And he was famous for saying, he said, sometimes a lie tells more of the truth than the truth. And sometimes the truth is really complicated, really hard to understand. In order to use it, I need an approximation. And the approximation is a bit of a lie. It's not quite the real thing, but it is the term I use, strategic simplification. It is a simplified description that will help us understand enough of the problem so we can solve problems with it. And so it's a practical approach to taking these very complicated equations and then
we should move on to the next picture, because I don't want to take too much of your time. And
but you can tell, you push my play button, and I think this is the most profound kind of concept
I can see
there is in the universe.
So basically what you are saying, in the bottom picture, there will be kind of 50 ohm resistors traveling to the moon. So it will actually create the circuit immediately after the switch is on.
Yeah, and not only that, but in the bottom picture over here, let me get my pen back. In the bottom picture over here, when we throw that switch, let's see. So between here and here, there is initially, before I throw the switch, let's see. This is 0, 0 over here. So there's no voltage between the two conductors. Over here, there's 1 volt between the conductors, and let's see. When I throw that switch between here, that voltage is going to drop. I'm going to actually have signals propagating in two directions. I'm going to have, let's see. This is going to be the plus voltage here, and so I'm going to have current flowing this way, propagating like this, and then over here, I'm going to have it the other way. It's going to take a while for the current to go this way, but I'm going to get current flowing in this direction pretty quickly. Let's see, actually, it goes this way. It goes signal return this way. So I'm going to get current flowing pretty quickly initially, and because of this LED is in close proximity to where the switch is, as soon as I throw that switch, I'm going to get current flowing this way.
But the current is going to be limited, or is going to be based on the impedance between the two wires.
Yes, and that instantaneous impedance is related to their separation and the material around them. And that is what we call, if it's uniform, long and uniform, we call that instantaneous impedance, that one value of impedance characterizing the transmission line, we call it the characteristic impedance. And so the current that's generated, my drawing here was a little messed up here, so let me redraw it here. Oops. So I'm going to get current flowing this way. I'm going to get current flowing, signal return this way right at the switch. And if this LED is located very close to that switch, these currents are going to flow initially and get to the LED and signal return and signal return and signal return. It's going to happen pretty quickly. If the LED, if I move this LED way over here, it's going to take finite time for that signal return, signal return, signal return to get over here and then go through the LED. So the physical position of that LED relative to where the source is, I'm calling that switch the source, that's what determines when the LED turns on.
What I'm thinking about is like
yeah,
on the bottom one. So
yeah,
if the current is kind of flowing through the space between the wires, this current may be
part of the current is displacement current is.
Yeah, but it may be different value as
well.
if it goes at the end, no? Because end is short circuit, then
oh, so you're saying, well, wait a minute, we got this oops, sorry, let me get my line back. We got this displacement current here, signal return, signal return, signal return, signal return. What happens when it hits the end here? Okay. Well, remember, this signal sees this instantaneous impedance of, if it's a 50 ohm, 50 ohms. Each step along the way, it sees 50 ohms, 50 ohms. And what does that mean? That means when I step and I increase this voltage here by 1 volt, it takes 20 milliamps of current flowing between the signal and return.
Yeah.
That's what that 50 ohms means. And it sees 50, 50, 50, 50, 50. It keeps on propagating 50, 50, 50. And now when I step right here, what impedance do I see? What is my instantaneous impedance?
0.
Yes, exactly. And now we have to invoke another important fundamental property of signals propagating on transmission lines. And that is this idea of reflections. And so whenever the signal sees a change in that instantaneous impedance, it reflects. And the reflection coefficient is going to be the second guy's impedance minus the first guy over their sum. So I'm in 50 ohms, and then I go to 0. What's the reflection coefficient? The second guy is 0 minus 50 ohms, the first guy, divided by the second guy is 0 plus 50 ohms. So what's that? Minus 1. So if 1 volt goes in this way, the reflected signal is minus 1 volt. And I have to take that into account. So what's the current? Now comes the question, well, what's the current? I had 20 milliamps of current, displacement current flowing over here. How much current do I have flowing through that short? Okay, I'm going to preface that by saying, this is a trick question. So when I do this to my students, I go, wink, wink, nudge, nudge, trick question. 20 milliamps is flowing down in displacement current, getting over to this point. How much current flows through that short? It's very, very subtle. And this is where you have to have some basic fundamental understanding of signals propagating on interconnects or on transmission lines. So I'll walk you through what happens. I'm going to clean up this figure a little bit. And we're just going to look at what happens right before this short. Right before the short, I've got my signal propagating in the, we're going to call this in the forward direction. This is the forward direction. And it's a 0 to 1 volt signal. And we said that's 20 milliamps. What is the current doing for that forward direction current? Well, it's going signal, return. It's rotating in the clockwise direction, right? Circulating in the clockwise direction. And it's 20 milliamps right when it gets to that interface where the short is. Okay, now it sees the short, and the reflection coefficient is minus 1. So that means that I'm going to have another signal generated that is going to propagate in the backward direction. and it's going to go this way, and its voltage is minus 1 volt. What does minus 1 volt mean? That means between the signal and the return, I have minus 1 volt propagating in the backward direction, right? So what's the direction of the current propagating this way? It's return signal, return signal, return signal. A negative voltage has current propagating in. So here's where we have to keep straight. We have to introduce this whole new concept. Current has two directions associated with it. It has a direction of propagation. That's the wave front. What direction of propagation is either forward direction or reverse direction. And it has a direction of circulation. If it's a positive going signal in the forward direction, it's signal return, signal return, signal return, clockwise. If it's propagating in the reverse direction, positive, it's signal return, rotating in the opposite direction. Right? So depending on, so if it's propagating this way, it's a signal return. If it's propagating this way, it's a signal return. This is a clockwise, this is a counterclockwise rotation. Still a positive signal. Depending on which direction the wavefront propagates, it circulates in a different direction. And if I had a negative signal going this way, the positive signal is signal return. A negative voltage is going to be return signal. That's rotating in the counterclockwise direction. They're both propagating in the same direction, but they're circulating in opposite directions because of the wavefront. We have to think about that wavefront of displacement current that connects the conduction current in the signal and the return. And so here's our negative signal that's propagating in the backward direction. What is its current doing? It's rotating, circulating in the clockwise direction. It's return signal, return signal, return signal. It's going in the clockwise direction. And so what do we have right here at the intersection? We have two wavefronts. We have the incident wavefront of 1 milliamp, I'm sorry, it's 20 milliamps in the clockwise direction, and we have a reflected signal that's going in the opposite direction, and it's 20 milliamps, and it's circulating in the same clockwise direction. Yeah. Oh my gosh, they're in the same direction. And so what is the net current right here at the short? It's 20 milliamps going in the clockwise direction, plus 20 milliamps reflecting in the in the clockwise
so it's
direction.
40 milliamps.
That's 40 milliamps. Wait a minute. I only had 20 milliamps going. Where did the 40 milliamps, the extra 20 milliamps, come from?
Because 2 volts.
Ah, very good. Because at my source, I had 2 volts with 50 ohm line, and that allowed me to launch a 1 volt signal into the line at 20 milliamps. But now when I have the short over there, this is now a short, after the reflection has hit the end and then come back, it's 50 ohms into 50 ohms, no reflection anymore. It's 2 volts with 50 ohms and a short. Of course, it's 40 milliamps to that 50 ohm resistor. This is how we use the properties of signals on transmission lines. Now, I didn't invoke anything about propagating electric and magnetic fields and solving a differential equation to give you the boundary condition where the electric field increases in different directions. I didn't invoke any of that. I used a simplified approximation based on a few rules. And one of those rules is signal propagates if it sees the same instantaneous impedance. A signal sees an instantaneous impedance, and when it encounters a change in impedance, we get a reflection based on the instantaneous impedances. And so we simplify the problem based on what we're kind of familiar with. We take one leap up from behavior of simple circuits and introduce this idea of a signal on a transmission line and how it interacts with instantaneous impedances. And it doesn't matter whether it's a lumped circuit or another transmission line, the behavior at the interface is the same. Well, let's go back to our case of the Earth to the Moon coax cable and our ohm meter at the beginning. When I launched that, when I connect my ohm meter to the beginning of my coax cable, my really long coax cable here, when I connected the ohm meter to the beginning, I had no idea what was going on at the end of that line. I saw 50 ohms because I went 20 milliamps in. If it was open at the end, the reflection comes back, cancels out that current, and 2 seconds later, I see an open.
Mm-hmm.
Suppose that I have a short at the far end. I get the reflected signal, the -1 volt coming back, and now what impedance am I going to see? I'm sorry, what resistance am I going to see at the beginning of the line with my digital ohm meter?
Oh, there will be 1 volt minus 1 volt.
Yes, I'm going to see 0 volts across there. And so, yeah, I have 20 milliamps of current because I've shorted out my digital multimeter, but there's no voltage across the device. I'm going to see 0 ohms, which of course is what I should, because it's shorted at the far end. And so what's
but
confusing
current
is
still flows there.
Because it's shorted and my digital multimeter, my ohm meter, has a voltage source on the inside and a source
Makes
resistance.
sense. Yeah.
And so I would see, as a function of time, the input impedance 50, and then it goes to a short 2 seconds later. So we have to keep in mind that because of the finite speed of light, the distributed nature of the transmission lines, the input impedance of a transmission line is time dependent. It changes. It is not intrinsic. It depends on the length of the line and what happens at the other end. And if I connected a 50 ohm resistor at the other end of the transmission line, what would my ohm meter see? So we've looked at 2 cases here.
50 ohm all the time.
Very good. So we said, here's the open. And now if we have a 50 ohm resistor at the far, no reflection to come back, I'm always going to have 20 milliamps going in, 20 milliamps. I'm going to see a constant instantaneous beam. And suppose I came to the front of my ohm meter and I just connected a 50 ohm resistor. What would I see?
In the front of my
ohm meter, my handheld digital ohm meter. I connect a 50 ohm resistor in front of it.
And we still have this long transmission.
I took the transmission line off. I just stuck a resistor there. Just put a resistor in front of my ohm meter. What do I measure as the impedance or the resistance?
Resistance.
This isn't the trick question.
No.
Yeah, I measured 50 ohms. And so here are 4 cases. I have an open at the far end. I see an open eventually. Initially, I see exactly the same thing happening in all 4 cases.
Mm-hmm.
At the far end, if it's open, eventually I'll see an open. If it's shorter at the far end, eventually I'll see a short. But if I have 50 ohm resistor, it will look identical to, if I have a 50 ohm at the end of the transmission line, it will look like a 50 ohm resistor initially, and it will look like a 50 ohm resistor forever. If I'm limited in doing a measurement in a time short compared to the round trip time of that transmission line, I cannot tell the difference. Mm-hmm. There is no measurement I can do between looking at the beginning of a uniform transmission line or looking at a discrete resistor I pull off the shelf. That's why we say a transmission line, if I look for a time short compared to the round trip time, a transmission line looks like a resistor at the front of the line. And that's what we'll see if we do a TDR measurement.
Okay, so make conclusion. What we are going to see on the bottom circuit?
What are we going to see on the bottom circuit?
Yeah.
If the LED is spatially located next to the switch, when I throw that switch, the LED is going to go on the same time I turn the switch on.
But not, is it going to be like on same current as when it arrives at the end?
Let's see. Okay, so initially, so that's a really good question. And the answer is no. It's going to be, let's see. I'm going to get reflection from this. I'm going to get the instantaneous impedance is going to be related to the voltage divider of the source resistor and the impedance of the line. So it could be half the current, something on that order.
Okay.
And then it's going to hit the end and reflect, and we're going to get current going this way. It's going to hit the end over here and reflect. We're going to have all those multiple bounces. They're going to take some time to occur. And eventually, when they stabilize, I'm going to have twice the current.
Okay.
Yeah.
I think we spent all our time talking about this.
That's okay, you know. And you, like my wife says, you know, you push my play button and I just keep on going. So, you know, because I think this is so interesting stuff. And it gives us they're little puzzles to solve. They're opportunities to exercise our understanding to real world problems. And they're, we're all engineers. We love problem solving. And each of these kinds of situations are little problems to solve. And so, that's why we do this, because it's fun.
Okay. You wanted to mention this free access through your coupon?
So I have a special deal for all of your viewers, because you and your viewers have been so patient in listening to some of my long-winded explanations. I wanted to offer you all a 3-month free complimentary subscription to the Signal Integrity Academy. So if you listen to my explanations and you want to hear more, I used to go around the world literally teaching short courses on signal integrity and power integrity, EMI. We recorded all of them. They're posted on the Teledyne LaCroix Signal Integrity Academy website. And normally they're for subscription. So you sign up and you pay money and you view them. But as our appreciation and for your patience in listening, I'm going to give you you go to, here's the shortcut. I'm going to write it on the screen and you can put it in the show notes. So you go to www.bethesignal.com, and that's the Teledyne LaCroix Signal Integrity Academy. And then under the menus there, you go to subscriptions and you look for the 3-month subscription. You fill out that form and ask for a promo code. And for viewers of your YouTube videos, all you do is you type in FEDSI. That's the promo code. You type that in, you fill it out, and that will get you a 3-month complimentary subscription to all the videos, all the courses that I've done on the
Wow.
over the years. So a great deal. As a kind of thank you for your patience in listening, sitting through all the things I've been saying here.
Thank you. Thank you very much, Eric.
So yeah, feel free to pass it on to any of your viewers, even on your website with the course subscriptions, which are really wonderful courses, and I heartily recommend them.
Thank you. So next time we will do the TDR.
Yes.
I
will try to
do it today.
To talk less. But you know what? We've set the foundation.
Yeah.
Because now we have what I think are the most important fundamental principles of signals on interconnects and how they propagate.
And that's everything for today's video. I would like to say thank you so much, Eric, that I could ask these questions. And I would like to know what you think about this topic. Leave comments. If you like this video, don't forget press like button. If you would like to see my future interview videos and other videos, don't forget to subscribe. I would like to thank you very much for watching and see you next time. Bye.